All right, so do those two sequences match? When we are comparing them as if they were amino acids, so you guys are pretty split. You're like, oh, I don't know, do they match or not? Let me show you the answer to this. Next one. All right, so what I did here was I gave you one sequence and I said, translate this. And I didn't tell you that you have to reverse complement. So we're going to say that this is the coding strand of DNA, and we do it in frame 1. So you read CTG, and you're just going to flip that C by U. If this was the coding strand, then your mRNA would be CUG, so leucine, L. The next one would be ATA, that's the isoleucine. Then, okay, GCG. So you just go each 3. And then the next one, I said, translate this as a frame 2. And then you might ask, how did you know it's frame 2? Oh, because I just came up with some sequence. This was just an opportunity to tell you about 2 frames of translation. There are 3 frames of translation for each strand of DNA. And I just came up with something that I on purpose wanted the frame 2 of this to match the frame 1 of this. The purpose of this exercise is to show you, even though these 2 DNA sequences wouldn't match when I compare them as nucleotides, so if I did a nucleotide blast, they'd say, no, they have nothing in common. But if they were protein, then they would have the same protein sequence. In real life, it's not always like a perfect match like this. This is just a toy problem, meaning I manipulated it to be very visible, like, oh, look, they are the same thing. So you're like, oh, how did you get this to be a leucine here? So I said skip the first C because I said it's frame 2. That means start translation on the second nucleotide. So TTA, we're going to say this is my coding strand. So it'll be UUA will be the mRNA. So UUA, that's leucine. And then you go down the next 3. So TTA is the first one, and then ATT the next one. Anyway, that ended up with that. And then you're supposed to say like, yeah, the 2 of them match. And you're like, all right, big deal, what is this for? And this is one of the reasons why you'd want to run something called tBLASTx. So what the tBLASTx program will do is it will take, let's say this is your query sequence. Takes your query sequence, translates into 6 frames. The 3 frames, the first 3 frames will be frame 1, and then frame 2, it skips the first one, and frame 3, it skips the first 2 and starts the codon here. So yes, Jackson, you have a question?
Yeah, I'm sorry, maybe I missed it, but where is the LIAF coming from?
Oh, these are the different amino acids that are encoded by this. So in frame 1, these first 3, they encode the leucine. So you're going to look up this triplet, this is a codon, in the genetic table, so in the genetic code. So you're going to say CTG, what does the DNA sequence CTG encode? And we're assuming that it's the sense strand, that's the coding strand. So it will go C, U, G, is that L? So that the L is for the leucine. And then you're going to go to the next one, ATA. A, there's no T, so you're going to use a U. A, U, A. So the isoleucine. So that's that I. And then the A will be the next 3. So first 3, second 3. The third codon will be GCG. So G, C, and then G is the last one. GCG, A for alanine. So that's where that is. The from, and then the F is phenylalanine is the fourth one. So first 3, second 3, third 3. This is my fourth codon codon encoding the fourth amino acid. So UUC, so TTC, we're going to read it as UUC, and then phenylalanine, the one letter word for phenylalanine is F. So if you didn't know that part, you can look this up. So amino acids can have either one-letter codes or three-letter codes. So this table here showing you the three-letter code, and then in my answer here I put the one-letter code. I could have written it down as the three-letter code. So hold on, there's a question. Yes, so about the BLAST1 due date, we'll see how far we'll get with this. I just wanted to finish this exercise and then we'll see how much time we have. Okay, so yes, Jackson.
Sorry, just to follow up, is there ever a time when we'll have to translate and then use that chart? Because that's what I initially did, and I think that's why my answers were all messed up, because I translated that the little bit of DNA code and then use the chart.
You mean you've reverse complemented it?
Yes.
So that would be if I said this DNA sequence is the template strand, then you would want to reverse complement it. And in fact, BLAST does that. So I mentioned something about translation in 6 frames. I showed you the 3 frames that it would translate this DNA sequence, but it doesn't assume that this is the coding strand, as I am assuming here just for simplicity. It also reverse complements this, meaning maybe this was the template strand and the mRNA is the sequence that is complementary to this. So then BLAST reverse complements that and then translates that reverse complement. Will I always tell you if it's coding or template? If I don't say anything, you can assume that this is the coding one, not the template. And if I'm trying to make you do more work, then I'll tell you it is the template. But in reality, you are going to run BLAST, and BLAST is going to do this work for you. It's going to do the six frames of translation. So what I wanted to show you with this exercise is that these 2 sequences, they don't match. You compare them as DNA. But if we had made them, you'd actually have 6 possible proteins here, 6 possible proteins here, and then you'd compare, does any of these 6 possible proteins from here, does it match any of the 6 possible proteins from this? And then I just directed you to do some specific frame because I wanted them to match, because I wanted to show you, look, there is some frame where they do match. All right, so I'm going to go back up to the next question, which is this one. And, well, I guess we are here on you already saw the answer. But I told you that BLAST takes our DNA sequence and it says, what are the 6 theoretical proteins it could generate? And then it tries to match those 6 that you input with other 6 from the database, or if you're doing a BLAST2, the 6 that is the second entry that you put. But one thing it doesn't do is you give it a protein sequence, and then it goes back to, what if this protein sequence was DNA? What DNA sequence could it be? So if you look up on this chart, then you'd say, okay, methionine, it's AUG. So you'd have to go oh, here's methionine, AUG. There's only one possibility. Great. Then tryptophan, where's TRP? Here it is. So here's tryptophan. What encodes tryptophan? UGG. Great. Okay, tyrosine. There are 2 possibilities. So in red, here are the answers. So if you look for tyrosine, there are 2. These are called codons, CODONS, S. So 2 different codons encode tyrosine. Often it's the third letter that changes. It's called the wobbly theory or wobble theory. So there are 2 possibilities for tyrosine. For leucine, look at that. There are so many different codons that could encode leucine. There are 6 possibilities. So over here. And then cysteine, there are 2 possibilities. So with this, what I wanted you to see is in a very short, this peptide, so this is not even a protein, this is too short to be considered a protein. Proteins are, there's no hard rule, but you think it's over 90 amino acids is a protein, shorter than that is a peptide. So in this peptide here, so some chunk of protein, there are, and I do ask you these types of things, how many possibilities of DNA sequence would there be to, yeah, about over 90 is a protein. I don't know, there's a hard rule. This is kind of what I was told. But basically, we think about proteins as longer and peptides as shorter amino acid sequence. Okay, so this peptide here would have how many possible DNA sequences that encode that? And then you'd say, okay, there's one codon that encodes methionine, one codon that encodes tryptophan. There are 2 possible codons, so this sequence or this other sequence, they both could encode the tyrosine there. And then 6 for leucine. So when I ask you, how many different DNA sequences could have encoded this peptide, what you're going to do is see how many codons there are for each of these amino acids and multiply them. And you see for this very short, is only 5 amino acid sequence, there would be 24 possible DNA sequences. Now imagine that this amino acid sequence is now only 5. This could be 100 amino acids, which is not an unreasonable number. How many DNA sequences? I don't know, hundreds, thousands. So BLAST does not go from protein to nucleotides, but it does go from nucleotide to protein because each nucleotide sequence can be translated into up to 6 proteins. Yes, Jessica?
Hi, sorry, I'm a little behind, but I'm still trying to understand number 3.
Mm-hmm.
For the amino acids that like the codon's coded for, how did you get F? Because like when I do TTC, I don't see where you got F from.
So this has to do with, I knew the 1-letter amino acid for phenylalanine. So TTC is, if this was the DNA sequence, then, and if it was the coding strand, then mRNA would be UUC. So you go UUC, and then that PHE is phenylalanine.
Okay.
So, and phenylalanine is abbreviated as F when we use the 1-letter code.
Okay, gotcha, thank you. And then also
You're
the second one, do we skip the first nucleotide because it's frame 2, or like will you tell us to do it? How do we know to do that?
Yes. I will tell you which frame I wanted to translate something. So if I tell you frame 1, frame 2, or frame 3, then you will know to start reading on the first, second, or third nucleotide. There isn't a frame 4 because a frame 4 would mean that you start reading here, which is the same thing as a frame 1, right? The frame 1 has this as the first codon, and then this is the second codon. So there isn't something called a frame 4, but we have a frame 1, a frame 2, a frame 3, and you're like, okay, how about the other 3? The other 3 come from reverse complementing this and translating the reverse complement, and they are called, you're going to see in an exercise in BLAST in the future, they are frame -1, -2, and -3, which means that that sequence got reverse complemented and then translating those other 3.
Great, thank you
So
so much.
good?
Mhm.
You're welcome.